Thank you, Carlos, and everyone for putting together this nice program. I'm sorry that I'm watching things on a different time, but I've been following it slowly. So again, thank you very much. The title of my talk is Nanoscale Thermal Machines, from Classical Kinetics to Quantum Coherences, and I hope it indeed fits to this program. So yeah, my name is Dvira Segal. I'm from the Departments of Chemistry and Physics at the University of Toronto. And in my talk, I'm going to focus, can you see my mouse? I'm assuming, yeah, I cannot see response.
Yes.
Okay, yes. Okay, great. So I'm going to focus on this simple thermal machine as a case study. So as you will see, it's hard to come up with general conclusions about the role, say, of coherences in quantum thermal machines. So I'm going to build up the discussion on a case study, and hopefully from there one could generalize or at least understand the different scenarios. So the small machines that I'm going to consider is what we refer to as a quantum absorption refrigerator. In this picture, it's quantum because of, as you will see also later, a simple reason. So just because it's the system is quantum in the sense of being discrete, of discrete energy levels. And the objective here is to, it's a cooling machine. The objective is to extract heat from this cold cloud, which is whatever, a thermal bath, and then dump this excess heat into this red cloud, which is a hot bath. And obviously, in order to achieve this task, we need to supply to do some work. And here it's done in the form of an additional heat bath, this T sub W, and W is for work, but it's really just a heat bath. So as you can see, in a cooling process, we are going to absorb heat from the cold bath, assisted by the work bath, and dump the total heat, the total energy into the hot bath. And obviously, there is also the reversed process, but this is the arrows depict the cooling scenario. So I will talk about this machine and, of course, some generalizations to it so as to examine the different questions about the role of coherences. How do fluctuations behave in the system? Why do we study fluctuations? What can we learn from them? A little bit about strong coupling. And when I say strong coupling, I mean the interaction between this quantum system and the surroundings, the different bath. And people have been active in looking at many other different effects. The last line here, which I'm not going to ask to focus on here, what happens if the baths are non-thermal, finite, if they are finite size, non-Markovian memory effects in the dynamics, and so on. So before I begin, just to let you know where I'm speaking from. So I'm at the University of Toronto, which is here, as you can see, at the very south of Canada. So indeed, most people are familiar, well, maybe with British Columbia, that's the west province of Canada, and then maybe with Ontario and Quebec, the east ones, but yeah, maybe you will be surprised there is something in between. So several, at least before I moved to Canada, I didn't know. So there are a couple of provinces here in between. So I spoiled it. Toronto is really nice in summer. It's absolutely beautiful. I invite people. I would be happy to host you here. So that's a picture from summer. It's also quite nice in winter in a different way, quite lovely. So this is a picture at the bottom from just last week. Okay, so to our business. I have two slides with just a broad discussion over my research group, leading to what I would like to tell you today. I'm not sure about indeed the audience, how broad and what's the level of the audience. So again, just an introduction. Broadly, the research of my group is about open quantum systems. So here you see this illustration with a system made of these lines that are whatever electronic states, vibrational states. And so these are quantum states, and the system is not isolated. That's the part which is open. It's exchanging energy with possibly different environments. So that could also be a non-equilibrium setting with different temperatures or different chemical potentials. There could be many body interactions in the system, in the way it's coupled to the environment. And obviously, we are also interested in the role of fluctuations. So Hamiltonian here written is a general starting point for many of our studies. Hamiltonian would be the sum of the systems Hamiltonian, the bath, and then there is a system-bath interaction, which for such nanoscale machines cannot be ignored, unlike macroscopic thermodynamics. So very quickly, just to show some examples related to my research, there are many great people studying open quantum systems. In my group, some focus has been on quantum systems where this entity is a molecule. Yeah, I'm a chemist after all. So the molecule, there are nice experiments about charge transport through single molecule devices. So the molecule here would be the quantum system if it's discrete electronic vibrational levels. And the bath would be the metal leads with different chemical potentials and even temperatures. There are other nice experiments in optoelectronics where now the quantum system would be in the form of a quantum dot, and the environment could be, besides the fermionic leads here, the source and drain, also the radiation, electromagnetic field, and other experiments also in the context of single molecules about vibrational heat flow. So that's, again, the quantum system would be the collection of vibrational levels of the system. So let me lead you again through a couple of projects in my group where I would like to show you evolution of ideas, and also how we started to think about the fluctuations, because that's going to be part of my discussion today. So thinking about charge transport, which is actually not going to be what I will focus today, as you could see from the first slide, but it depicts the main idea. When you look at such processes, maybe you will begin with the simplest quantity, which would be linear response observable, just the conductance, electrical conductance. And from there, you would move, let's say, to non-equilibrium scenario, and that would give you the charge current. So that would be the current voltage characteristics for charge transport. And yeah, in my group, we have been looking at, there are many other people are looking in at such problems. Suppose I have a lattice, or one-dimensional or beyond, and each unit represents whether it's a monomer or a site in a lattice with local interactions possibly, and thinking about the different transport mechanisms that such a system could support. And in our studies, this quasi one-dimensional or periodic system could be, for example, a DNA molecule. Moving from measures such as linear response conductance and IV characteristics, we moved in the last, 5 or more years to look at the noise associated with the current, or the fluctuations associated with the current. So I will not dwell on this part of my research, but we very fruitful collaboration with an experimental group. They can measure electron current noise, and the question is what information is conveyed in the signal, in the noise that they measure. So moving indeed to questions about noise, on the one hand, I just told you, it conveys some information about the underlying effects, whether interactions or the non-equilibrium setting. Furthermore, and that's item C here at the bottom, in the past 5 years or more, there has been a huge effort in our community in trying to understand trade-off relations in the context of minimal models for stochastic, classical, or quantum thermal machines, where the idea, and this is taken from this study, the idea is to find trade-off relations that involve not just the power and efficiency, but furthermore fluctuations. And this area, sometimes coined the thermodynamic uncertainty relations, it started in biophysics and classical stochastic thermodynamics. And in my group, together with Vijay Agarwala, maybe is in the audience, we pushed it to the quantum regime. So this brings me indeed to sort of summarize my thoughts about why study noise, whether in electronic junctions or in the context of the absorption refrigerators. I will be back to my absorption refrigerator soon. So let me just tell you several ideas that I have, why noise is useful to consider. Indeed, when we started about 10 years ago thinking about it, it was purely from the theoretical point of view, where we had developed a certain technique to study quantum dynamics, quantum transport. And obviously you have to make some approximations, whether you do perturbative expansion of the system at interaction, or interactions are taken only in a certain simplistic way. And the question has been, after this effort, okay, you get a result, you do simulations, and you can plot nicely the current and as a function of a certain parameter, and you hope that it tells you something useful about the experiments or the physical system. And the question has been whether these theories that obviously, or calculations are not exact, whether they are thermodynamically consistent. So it's not just whether the numbers are correct or close to the exact result, but maybe I'm violating something fundamental. Yeah, so that brings us, of course, to the here's a steady state heat exchange entropy production fluctuation symmetry, where we started to think about testing this relation once we have a method that we have developed. Moving on to 2, so that's what I mentioned, together with an experimental group. Here we realized it's not just an academic game to look at noise and fluctuations and test the fluctuation symmetry, but there is information, in fact, conveyed in the cumulants in different moments of the process. So here at the top, you can see a simple depiction of, let's say, there is a probability distribution function to transfer big N particles in a certain time t. There is a mean, C1, and then there are these other characteristics of the distribution function, whether it's the variance or the asymmetry, and from there you can learn something fundamental about the system. And lastly, it's what number 3, what I just mentioned in the previous slide, that thinking about nanoscale thermal machines, we realize now that there are interesting trade-offs involving not just, again, the power and efficiency, but also fluctuations. And this is, again, the thermodynamic uncertainty relation that maybe I will mention in passing below, but it's not going to be the focus of my talk. Okay, so to the outline, I will have one slide of an introduction to quantum thermodynamics. I'm going to talk about the quantum thermal machine. So just to put it in the context of the community. And I'm going to focus on the absorption refrigerator. So I will reintroduce it again with some more details. And then as time allows, in my group, we have been looking at this model here at the top right with some extensions and probing these different questions about the role of quantum coherences. The question is, are quantum coherences helpful for the operation of this machine or not? Fluctuations, that's the next item. Again, we've had here a couple of studies where we looked at the fluctuations associated with the cooling current and how to calculate them, whether the methods that we use, again, are consistent, whether there are universal relations holding for these fluctuations, and we'll talk about some of them also, if I get the time at the bottom here. And finally, number 4, about the impact of strong system path coupling. And again, the question is whether it's beneficial or not to the operation of our machine. So that's my introduction to quantum thermodynamics. I'm just directing you to a great book, a collection of contributions from leaders in the community. As you can see, it's quite massive with almost 1,000 pages. Just by going over the table of content, you can get a sense of the different activities in the field, whether it's about quantum heat machines in part 1, fluctuations, questions of equilibrations, information theory concepts, and of course, experimental platforms that are more and more the focus of this community. Okay, so now to the quantum absorption refrigerator, the model I already introduced in my first slide. The model has been suggested many years ago, and this is an illustration from the original paper. It was suggested here as a maser, so operating in the reversed form instead of as a cooling machine, as an engine. But let me again focus on my illustration, which is just the same, but I think it's maybe more clear, or at least more colorful. So again, the system, the quantum system, the working fluid, as we say in thermodynamics, is this 3-level system. It's depicted here as big, but it's supposed to be the small component. And let me introduce a notation. So I'm going to refer to the splitting as a theta. So theta C cold corresponds to the lowest energy splitting, and then theta work corresponds to the top one, and theta hot corresponds to the total energy splitting between the ground state and the upper state. What one can show, and I will go with you over it because that's a part of my classical argument about this machine, is that very easily one can derive a cooling condition for this device. Again, I'm showing you with arrows the beneficial direction that I would like to observe here with the net effect of extracting heat from a cold bath. So the cooling condition that you see here on the right-hand side At the right side, it involves the ratio of frequencies. So that's this small frequency over the total one. And at the left-hand side, it's a combination of the temperatures of the different heat baths. And overall, the message is that if you want to cool your cold bath, this splitting theta cold has to be small enough. It's difficult to cool if you have a big transition, because the cold bath obviously cannot excite much this transition. So that's a general guideline. Yeah, theta cold has to be small, and that would allow you to cool the system. There has been very nice papers and even reviews in the community. So I encourage you, if you are interested, to dig more into this model. The top paper that I cite here is this is Annual Reviews of Physical Chemistry, already for some time ago. Both papers are actually from some time, and the second one was a very nice study where I took these pictures from. So just to show you that I'm talking about the panel A, this type of design. But there are other suggestions that actually correspond to panel A, different modifications. So one could show how these different settings map one to the other. Maybe I will mention just the panel C. As you can see here, the proposal is probably the most realistic, where the idea is that you have 3 separate qubits, or 2-level systems, and you are able to couple them with this G parameter, but the cooling operation is done on the, where each bath couples individually to each qubit. So that seems to be indeed more relevant for experiments. So here just a slide mentioning 2 out of couple of proposals, or even an experiment in this field. So at the right side, this is an experiment from 2-3 years ago with trapped ions. So without going to details, because we don't have time, if you can see, there are 3 little trapped ions here at the center, and the idea was to exchange energy between the different modes of motion of these ions. They can do this axial zigzag motion, or the radial zigzag, and the rocking, and some, depending on the mode, they are either smiling or sad. And the idea is to transfer energy, as you can see, from this mode, which was cooled down by the control field, and to dump the excess heat into the hot bath. At the left side, it's a totally different architecture and realization, and here it's based on, as you can see, Josephson junction. And this is a proposal. So just to make a point that there are suggestions and proposals and efforts to realize such machines. So now I would like to, for a moment, to just show you that we can do a lot with classical physics. And in fact, we can analyze the performance of these little machines fully in a fully classical way. So I'm going to use kinetic equations, what we often call master equations. So let's go over the simple derivation. So I'm going to denote the level populations by P. So P1 is a level population. Of course, it can depend on time, but I'm going to focus on the steady state behavior once whatever initial conditions have been here, we lost them. So P1, P2, P3 are going to be the, I think I'm immediately using, I wasn't careful enough. So these are going to be the populations. Let's write down the equation of motion. So the population dynamics, here it is. It's really just rate equations where, let's say, the population of level 1, there is a leakage because you get transition from 1 to 2 and 1 to 3. On the one hand, on the other hand, you get some population from level 2 and some population from level 3. So it's really just simple kinetic master equations that you can write down to analyze the population dynamics. And given that, you can also write down a simple form for what are the heat currents. So we mentioned that we would like to look at the cooling current. So let's take a look at the form of the cooling current. What it is going to be. So I'm just taking a look at the population of level 1 and the transition from 1 to 2 as due to the coupling to the cold bath. And I'm taking the difference from the opposite process, which brings me population from the top level. So this is really just the net flow. of a population to level 1, and then I multiply it by the respective frequency, which tells me about how much heat is going to be absorbed in this process. And these expressions obviously can be justified by proper, more fundamental relations. So we can put down these relations for the cooling current, the work current, the heat current. Everything is given. We can solve the dynamical equation in steady state, find the populations, plug them here, get the steady state heat currents. And from there, we can write down a nice expression, and this is already the steady state, the current in the steady state limit. The denominator, we don't need, I'm going to ignore right now, it's just a monster. But overall, yeah, we have something, a closed form expression for the cooling current. And with that, immediately, you can ask the question, well, what is the cooling condition? What should be the relationship between the rates or the parameters? So as I cool, I absorb heat from the cold bath. And here the convention of this, the sign convention is such that JC positive means extracting heat. So a simple massage of these expressions using the detail balance, forgot to mention it, between the excitation and relaxation rates, you immediately get this cooling condition that I mentioned to you before, how you should set the energies of the system so as to allow the system to cool. And from there, you can continue, you can look at the coefficient of performance, which is, you can think about it as a measure for the efficiency. And you can continue and, analyze it corresponding to Carnot efficiency. You can show that it's always bounded. And people have continued and looked at efficiency at max power, and fluctuations, and other relations here. So already from stochastic, my point is that thinking about it in classical terms and using stochastic thermodynamics, you can analyze many interesting aspects of this machine. So that brings us to the question of where is quantum mechanics here? So one point here is that these population dynamics that I mentioned, one can arrive to this result based on rigorous open quantum system formalism. So just to sketch it, if people are not familiar with it, you would begin with a quantum Liouville equation, and by doing perturbation theory to the system bath coupling, so assuming it's weak, and other assumptions standard to this community, whether Markovian dynamics or uncorrelated initial condition for the system and the bath, then indeed you can, for this model, you immediately arrive at the population dynamics equation without steady state coherences. And so where is the quantum? Where are the quantum effects? They are hidden here in, obviously the levels are discrete, but they are hidden in the rates. So the rate constants that I mentioned above as just, here is a rate for transition, for excitation or relaxation. Obviously that's where the information is hidden about the macroscopic effects, whether it's the spectral function of the bath or the Bose-Einstein distribution function. And this again can be derived properly as you walk in and can be written down. So with that, so that was about the classical description of this quantum thermal machine, the simplest one. You can gain a lot just from doing a classical kinetic analysis. So this brought us indeed a couple of years ago already with my former graduate student, Michael, to take a look at machines where we will observe steady state coherences. So in the steady state limit, in the energy basis, we are going to observe coherences between eigenstates. So the design that we considered here, well, maybe it seems artificial. One can come up with experimental realizations. The idea was to generalize this three-level scenario. I'm sorry that I changed notation here. I just took it from this publication. And what is a new design? So I have the ground state, the excited state. I didn't touch them. But in between, instead of level 2, I replaced it by 2 levels that are actually coupled to each other, talking to each other through this coherent coupling G. And this model, it's quite interesting. It also is related to a model that has been analyzed a lot in the literature, the V model, with applications for its own and interest by its own sake. So just to highlight the notation, in the what we call site basis, I have this A and B levels with the G, which is the energy parameter controlling the tunneling, splitting between them. Ignore this gamma D. I will not dwell on all the details of this study. And once I go to the energy basis, so I diagonalize, yeah, this A and B, I get the 2 and 3 levels with energy splitting 2G. And obviously, once I go to the energy basis now, the coupling to the heat bath are more involved. They are no longer local. Yeah, so it's something like global thermalization, and I see the heat bath coupled to different transitions in the system. And there has been just a comment and nice discussions in the last couple of years about the different bases with Geraldine, for example, publishing a very nice work on it. So questions indeed about, since we are not doing exact work here, we are using perturbative methods. The question is which basis, global or local, is more useful, is more correct? And what are you missing, yeah, if you're working the wrong basis? So I will talk about our analysis in the energy basis. And without too many details on the technique, because it's very, very standard, we use the so-called Redfield equation, which has a microscopic derivation right away from the quantum Liouville equation. There is a detailed balance relation between the transition rates. You do get to thermal equilibrium. In the correct limit, you reduce to the population dynamics equations that I mentioned above. There could be an issue with positivity, but typically not in the steady state limit, so that's not something that we're concerned with. And for people who are familiar with Lindblad equation, it's really the friend of Lindblad equation, but with a microscopic derivation. And microscopic, I mean that you put down the Hamiltonian, and you have to decide on the system bath interactions, you have to decide on the nature of your system, and you get you write it down and you get all those rates. Yeah, we'll skip those details. So what did we find? Just by this very simple approach, again, having these 2 levels where I know that in steady state, I should get coherences still alive between them. In terms of formal expressions for the heat current and population or coherences dynamics, everything is quite clear and set in the community. There are no fundamental issues here. So let me immediately tell you about simulation results. What are we observing here? So we are just using these Redfield equations for the equation for the model. So this is a contour picture where what you see here is a theta cold. I would like to remind you that's the frequency here of transition. That's a splitting between level 1 and B. And then G is this coherent coupling between A and B levels. And I forgot to put a color map, but where it's colorful, it means that the system is cooling. So when it's very bright, it means a great cooling machine. So as you can see, and this is obviously a log scale. So as you can see, for a certain range of this tunneling, for this splitting, the system acts as a cooler. When it's dark, it means that the cooling current is very, very small, negligibly small. And the strange shape is because outside this colorful region, the system just doesn't act as a cooling machine. So it actually operates in the reversed mode. Okay, so here is indeed the color bar, doesn't matter so much. But what I would like to contrast these results with what happens if we do the kinetic analysis. If we forget about coherences in the system, if we assume that they disappeared, it's sometimes called the secular approximation. And then what happens here, if you take a look in this region where the dark area, where previously we didn't have any cooling performance, suddenly it's very bright, which means that the system can cool. So this was all in correspondence to questions or to demonstrations previously in the literature, where typically people wanted to show that coherences were beneficial for performance of quantum machines. That, I guess, is more exciting than saying that quantum effects are not great. So there were a couple of models put together and analyzed showing beneficial aspect for coherences. And here we just pointed out a very simple, even trivial point, that obviously in quantum mechanics, we can also see destructive interference effects. And this is actually what is happening here. And that's why there is a cooling performance where it shouldn't be, because yeah, there was a destructive interference effect here. And in between, I will not dwell on all the details. You're welcome to check the paper. One can also investigate transition between these 2 extremes, the case with full coherences and the case where we take them away.
Sorry, Dvira, may I ask a question? So here the coherences are only in the system. The baths are not coherent.
Yeah, so these are, maybe I should show them the next slide, which I thought to omit, but actually, okay, this is for the related, I'm looking at the coherences between levels 2 and 3 in the steady state limit, so it's already at long times, as a function of this splitting G, and when G is small, as you can see, okay, these are the real and imaginary part, there is something. And when G is large, when the levels are tuned away from each other, meaning that the tunneling is large, then the steady state coherence goes to 0. Does it answer your question?
Yes, thanks.
And
Dvira, I also have one question. May I ask it now? So you say, so I find it very interesting. You say that here you may see a detrimental effect of quantum mechanics because because you expect that the interferences are destructive. But okay, could you really show that this advantage is due to destructive interferences?
So. Okay, I don't have here this picture of in the energy basis, maybe in the next one.
Or is it some interpretation?
It is an interpretation. What one can show is that indeed there is a path. The heat baths are now coupled to the two transitions, and there is a sign difference. It's not shown in this illustration, but in the coupling form of the heat bath to each transition, there is a phase. So it is an interpretation, but we can see how once changing this sign between the transitions, phase, I should say, we can turn the model from showing constructive interference to destructive.
Okay, and so I think this effect does not happen in the local basis, in the computer, in the charge state basis.
So yeah, the simulations were done in the energy basis. In the local basis, I'm trying to remember, we did perform those simulations. So you would get, I think, the same results when G is rather small, because they should agree, the local and global should agree when you are in this small G region.
No, well, when it's G is too small, I think global does not give you correct results. But okay, that's maybe too technical. I let you continue, but yeah, that's very interesting. Thank you.
So okay, we'll skip these details. I mentioned already something here. So actually that's about what I wanted to mention about coherences. Indeed, there are further details here about how one can play with these models, whether by suggesting different level arrangement or by hand, playing with phase of when you have two different, the heat bath here, it's the same bath which controls two different transitions from level 1 to level 2 and to level 3, but there is a phase, and I didn't show it, but when you do the transformation from local to global, you get this prefactor. So one can indeed show how the model can be turned between different, acting differently. I think Archak has a question if it's related.
Hi. So when in the previous case, when you when you had this this color plot with written secular, I mean, do you mean that you actually remove the coherences by hand, or did you actually tune a parameter in your setup to get rid of coherence?
So yeah, we did both actually. So I didn't want to dwell on it, but yeah, we have had this gamma D parameter which was supposed to which was decohering the coherences. So that was, as you can see, there is panel A here and panel E. So in between, we tune this parameter slowly, gradually, to show that you can arrive to it in a slow way.
Okay, thanks.
So with that, I would like indeed to move on and talk about coherence fluctuations in this model. So this was a separate study with Junji Liu, a former postdoc in the group. And as I mentioned to you, there are a couple of motivations to study the behavior of fluctuations here. Generally, it was to verify the fluctuation symmetry. It's difficult to measure heat currents, so obviously to measure the fluctuations, and it's not trivial. So here our main objective was first to make sure that with this treatment, red field, we more or less satisfy the fluctuation symmetry, so that was part of the discussion. And the other aspect, which let me say a few words about it, was the thermodynamic uncertainty relation. So this is it's written here in a simplified form, where J here is going to be, let's say, our cooling current, and the animal at the numerator, it's going to be the variance of the cooling current, so add to it the C, JC. Sigma is going to be the total entropy production. I'm talking only about steady state behavior, so that's in the steady state limit. That's of course the entropy production associated with heat exchange with the bath, because for the system I'm already in steady state. So this is a nice, interesting, intriguing trade-off relation between the uncertainty, as we call it, and the dissipation. Yeah, how much entropy production is generated here. And it was analyzed, as I mentioned at the very beginning, for classical Markovian systems. And one question that we have had here, along with other studies, is what do quantum effects do, or coherences essentially? What does it do to this relation? In principle, we would like to break it. If we can break it, it's a win for us. It means that you can operate your machine better with reduced fluctuations or with reduced heat dissipation. So we would like to get to numbers that are below 2, but again, it's a big field, and now there are generalizations to this uncertainty relation. So I'm sorry that I changed here the notations, because it was a different student and they had a different, instead of G, they used mu. But if we just focus on 2 lines, the green one, which is this secular incoherent limit, and the dark line, which is what happens when this G or mu now is small, such that actually I do have coherences in the steady state limit. And I'm looking here at the relative fluctuations. So when this coherent coupling is small, as you can see, actually fluctuations are a couple of orders of magnitude greater than in the green line. Here is when the system operates as a refrigerator, and here is when it operates in the opposite manner. So having coherences here, as you can see, is associated with way more fluctuations. On the other hand, once we put together the entropy production, and this is what we call the 2 ratio, so that's a full combination here at the left-hand side. This was quite interesting, and we didn't support it by theory. It was so far just a numerical observation. Those lines, they almost collapsed, definitely in the engine regime. They collapsed onto one another, showing that, whether or not you have coherences in the system, still this trade-off relation brings about the same result. So this is quite intriguing. We were still surprised by it, but maybe we'll go back to it. It was published about last year, and try to analytically see what could be the origin of this effect. So I don't have much time. I will skip this point. I will very briefly mention a recent study with Vijay from ISR Pune, just to give you something new. And I'm also hoping to get the community thinking about this inequality, and hopefully more people would be intrigued by it. So here you can already see the result of this recent paper. It's an interesting, as you can see, inequality with the efficiency of the machine. So if I'm talking about the absorption refrigerator, that would be the measure related to the efficiency of the cooling machine. And at the very end, I have Carnot efficiency, or the corresponding maximum efficiency. So, okay, efficiency is bounded by Carnot. I know these 2 ends, but in between there is something else, which is what we call eta 2. And let me get you through what is this eta 2. So this whole analysis was done, it's limited to linear response. The proof of this result is limited to linear response. So I have the currents, and they depend on, obviously, the affinities with these coefficients. And I have the currents. I can also define fluctuations, so the variance of these currents. Again, in my context, the currents could be the cooling current, the warm current, the heat current coming from the hot bath. And what we are going to furthermore define is relative fluctuations. So taking the ratio between, the variance and the averaged current square. And with that, we introduce a furthermore combined measure, which is a ratio of relative fluctuations. And the analysis was done for this measure. When we look at the operation of the system as a machine, a useful machine, whether a refrigerator or an engine. And the point was that when the system operates, when it delivers powers, one can prove based on linear response thermodynamics that this measure is larger than 1. And this, again, with very few steps. Actually, the referee complained that it was too simple, but I just don't want to go over it here. From this simple result, one can almost immediately find this lower and upper bound for eta 2. So eta 2, what is it? It's now I realize I didn't have it in the slide, sorry. So eta 2 is a ratio of fluctuations of, let's say, the cooling current and the work current. So the efficiency itself will be the ratio of the currents themselves, the cold current, the current extracted from the cold bath, and the current absorbed from the work bath. And eta 2 would be the same type of ratio, but for the fluctuations. And what is interesting, intriguing about this relationship, as you can see, it's a tighter bound for efficiency. So rather than just limiting it by Carnot efficiency, there is a tighter bound. Now, we were motivated here. I should give, of course, credit. There was a paper in the literature, and sorry, I don't remember all the authors, so where they started to look at this. They suggested this inequality. They tested it for a 4-stroke engine. And our contribution here has been to look at it for steady-state machines, continuous steady-state machines. So we were not the first to suggest this bound. We tested it for thermoelectric engines. I will not go over it, and also for the quantum absorption refrigerator. I just want to highlight that the proof was done in linear response. So when we test it, it's useful because we wanted to check what happens beyond equilibrium, beyond the close to equilibrium. So this is a far from equilibrium regime when the affinities are large, whether it's in the thermoelectric engine, high bias voltage and temperature difference is large, or for the absorption refrigerator, the temperature differences are going to be rather large. Okay, skip. So we use the absorption refrigerator to test this inequality, this bounds beyond linear response. Just a comment that this simple model that I mentioned at the beginning, which we could analyze even classically, the lower bound here becomes trivial in this system. There is a saturation. One can quickly do an analysis and look at the fluctuations of this model. And interestingly, or when you think about it, it's not super surprising. The fluctuations behave, as you can see, they are proportional to the current squared. So there is a very simple relationship, and therefore the lower bound saturates. And that brought us again to look at the 4-level model, which is not trivial, and to take a look and check whether these inequalities work. And okay, there are too many lines here if you forget about these empty lines with and just focus on the top one, which is a maximum efficiency for cooling here. The bottom one, which is efficiency itself squared, and this one, the red full circles, this is the eta 2, and clearly the eta 2 is sitting in between. So this was a fully numerical test. I mean, without, we don't have a proof to show that far from equilibrium. This should be true, but at least for the cases that we looked at and we tried to analyze it in broad regime, it holds. So that's where I'm bringing it to the community, and I would be really excited if more people are taking a look at these bounds here. Here they are again. This eta 2, which again is a ratio of fluctuations, and understanding the validity or violation of this relationship far from equilibrium. Yes, so that's indeed the main question. So I think I will, in the last 5 minutes, I will just mention the last aspect. So far I used this absorption refrigerator to tell you about coherences, which could be good or bad, to tell you about fluctuations a little bit, how we are using it to test relations, interesting relations. And finally, I want to mention something about strong system bath coupling. When we go to the nanoscale regime, we cannot no longer ignore the interaction energy. It can be a significant part of the total energy of the model, of the C setup. So yeah, one needs to start thinking how to develop techniques and how to do simulations with strong system math coupling. I cited here a paper from the literature. There are other studies. This paper specifically was useful for us in this principle of reaction coordinate. So in a couple of studies with my graduate student, Nick, very productive, we worked along this method developed here. It's called reaction coordinate. There is a chemistry context to that, but that's not so important. So what is the main idea here? Well, if I have my quantum system, maybe a two-level system for simplicity, and these balls are supposed to be modes of the bath, harmonic oscillator modes, let's say. And in this type of modeling, they are independently coupled to my system. So that's this connectivity that we begin with in our model. And there are many, of course. Yeah, many, it's going to be a continuum, and many red balls and many blue balls, and the different colors are supposed to correspond to the temperature of the heat bath. So the idea of this reaction coordinate is that if the system is strongly coupled to the bath, depending, of course, on the details, one could rationalize that maybe by absorbing some degrees of freedom from the bath into the system and creating a super system, I can then treat this super system as weakly coupled to the rest of the universe. So that's the idea. Some degrees of freedom of the bath, I can define such degrees of freedom. And they are referred to as reaction coordinate because they could be generalized in the form of a combination of the original coordinates. And these are possibly strongly coupled to the system. So now they are included in the model. So it's an extended quantum system, which is now the new boundaries. I redefine the boundaries of what the system is and what the bath is, and now I can do weak coupling with the rest. So it's a simple principle. It was explored before by Gernot Schaller, for example, Hassan Nazir, and others with beautiful studies. Our contribution here has been to push it to look at quantum thermal machines, quantum transport and quantum thermal machines, because previously most of the effort was on the dynamics. So let's take a look at this absorption refrigerator, and now we are going to allow these couplings to be strong. Again, I'm sorry, the notation is different. Every student, they have prefer a different notation for the model. So now delta is a splitting, and 1 minus delta is a top splitting, and lambda corresponds to the system bath coupling. And this is really just to depict the picture without going to the technical details, where big omega is going to be this frequency that I'm going to extract from the bath, this mode, and add it to my system. And similarly, I'm going to add one mode from the cold bath, again, a generalized mode. So it collects actually, it is built from many modes of the bath. And we did this transformation only to 2 baths, the cold and warm, but just because it was becoming a massive computational problem, we didn't extract a reaction coordinate from the hot bath. So I hope the principle is clear of why this should indeed allow us to take into account strong coupling. We've had I should have shown you, the reference, if you want to see more details, it was in this past year paper where we argued and showed how indeed we capture strong coupling in this with this technique. But quickly to the results, because I think they are quite intriguing. And it connects again to the question of the cooling window. So the color stuff is where the system is cooling. So remember, theta cold is a splitting here, and lambda is a system bath coupling. So the first calculation is done with weak coupling technique. So this is a Born-Markov-Redfield quantum master equation. It's the same population dynamics that I showed you at the very beginning of the talk. Just simple cooling condition that can be derived from population dynamics. And remember, the cooling condition was such that theta cold has to be, this one has to be small enough. So this is indeed what you see when it's small relative to 1 is a total, the system can cool. Now, in terms of the role of the system bath coupling, when you use weak coupling techniques, there is a very simple rule. Strong is good, which obviously is just because of the deficiencies of the problem. They don't treat strong coupling properly. So strong coupling is good when you do perturbative, lower order perturbative treatment, because as you cool stronger and stronger, you just, you can transfer more energy. You don't see any detrimental effects. So that's what you see here. just enhancement of the cooling performance as you increase coupling. This is, of course, what happens here is just incorrect. It's this is a prediction from weak coupling technique. And we moved on and used our reaction coordinate approach, where we absorb degrees of freedom from the bath. We have this super system, and now we study the performance of the machine. So what happens here? As you can see, I'm at, let's say, at a certain theta cold, and I'm checking what happens as I go to strong coupling, and I'm going outside the cooling region. Yeah, from colorful to dark here, it means no cooling. So here you would say, so strong coupling is not good, yeah, because I was cooling, and now because of I increased the coupling, I went out. On the other hand, if you are here, there is no coupling there is no cooling in this region, and now you increase the coupling strength, and you would be super happy. You would say, oh, strong coupling is beneficial. Now it allows me to cool when at weak coupling I didn't. So one message here was that in the literature, when we looked back, people looked at specific parameters and were either happy or not about the role of strong coupling. But the real advantage of this reaction coordinate is that we were able to perform such a massive simulation. And this was quite a feat. And then it allows us to take a good look at what is going on in this system. And we realize that the true physics is just renormalization of parameters. And that's why the cooling window is, as you can see, from weak coupling, it aligns, it reshapes, because one can capture it with, indeed, by analytically showing how parameters are renormalized. So the cooling condition, one can still write it in a very similar form, only that the energies now that has to be analyzed for the cooling condition are not the original bare energy levels, but now they depend on the coupling, original coupling strength, and we have this analysis. It's not in the archive paper, it's still in preparation. So that's one message about strong coupling, not necessarily good or bad. It just changes your cooling window because of level renormalization. So with that, I would like to summarize. We are using quantum absorption refrigerators as a test bed to analyze different aspects in quantum thermodynamics. And here, okay, for coherences, we demonstrated a destructive effect. Of course, it's not a general rule. It's model dependent. Fluctuations, we found that there were more fluctuations when coherences were large. I don't think it's general. It's but the tour itself, the thermodynamic uncertainty relation was quite insensitive to coherences, still intriguing. And finally, strong coupling, we argue that the prominent impact is it's a reshaping of the cooling window because of a parameter renormalization. So lastly, I should have done it at the beginning. I would like to acknowledge the members of my group. Who should I begin with? Maybe with Vijay from Pune, a great collaborator. I'm really thankful for all our interactions. Junji Liu, a former postdoc, and Ilya in my group. And not everyone actually is in the group. People have already graduated. It's from September. It's one of these rare occasions in the pandemic where we could actually come together. So we took a picture. And thank you very much for, again, inviting me for this opportunity.
Thank you very much, Dvira, for this very nice talk. And I forgot to say at the beginning, thank you very much for being here, even though it was so early for you in Toronto.
No, it's okay.
So I have many questions. I see questions from the audience, so let's start with them. Please, Alberto.
Thank you, Dvira, for your very interesting talk. I have a question about the bounds that you have shown. You have shown a bound for the efficiency and one for the fluctuation. So my general question is, when are these bounds saturated? For example, those for the fluctuations, in particular with respect, say, to the extracted power or the efficiency. Or in other words, are those bounds saturated where the machine is sort of useful machine, so the power and or the efficiency are finite in a sense?
First, I should mention that these bounds were derived assuming the machine acts as either of these three scenarios: heat engine, refrigerator, or heat pump. Mm-hmm. for this, the maximal efficiency, of course, depends on. So it has to be within this different operation regime. This was part of the analysis. The proof relies on the machine operating in this either of these forms. Regarding saturation, so here it was in the tight coupling limit, the lower bound. So proportional,
In this case, you showed a curve of the efficiency and the bound, here, and then the efficiency goes to 0. So the efficiency square goes to 0 when you
this is when I leave the cooling window. So this is already, it's not unlike the 3-level model here. Actually, as you can see, I don't approach the Carnot efficiency because there are competing cycles here. So when one cycle wins, the other one doesn't. So that's why this model is way more interesting than the 3-level model. I should have shown maybe the 3-level, and over there you do saturate bounds. But the 4-level model, it's called internal dissipation in the sense that the cycles compete. So there is always some dissipation. You cannot, when one is doing its best, the other one destroys your optimal performance because it's not optimized because of the different splitting.
Yeah, and in the case of the upper bound a lower bound for the fluctuation. So how far or how close are you to useful regime?
Yeah, okay, I see. Whether we can say something about when is it? I don't have. So maybe not what you are asking, but maybe a side comment. We looked actually at generalizing this bound. What happens if it's not just eta 2? It's not just a ratio of fluctuations. And it's really, I don't think people can measure it, but higher cumulants. So now eta to the n means the third, fourth, and third cumulant. And we showed that there is this hierarchy, and actually the second cumulant was the best. So the 2 was the tightest of the others. But this is it was a specific limit. It was not general. But there was an additional analysis that we did in this paper that is now almost published in Journal of Physics Mathematics. And it was indeed about more details on the absorption refrigerator and trying to tighten the bound.
Just because, also from conversation with other colleagues, I have the impression that this limit or these bounds are saturated far from the useful regime where power is, for example, is finite in these microscopic machines. But it's
at least here you at least here you see that the maximal efficiency is way above. It still gives, it's closer to definitely to the efficiency itself. So it does give a title. Bound.
Okay, thank you.
Sure.
Geraldine.
Yes, thank you, Dvira, for this very nice and interesting talk and clear. I have one question also related to this efficiency eta 2, and in the slides where you define the different quantities you were using, the first one, you introduce this ratio Q between uncertainties of the two currents. So I guess these L11 and L22 are the Onsager coefficients for charge and heat currents. Yes. And but how do they relate? How does Q relate to eta 2? I missed.
Sorry, I skipped. I don't think I brought this slide. Maybe I have a backup slide. There were a few steps over there. It's there are some manipulations that one does to get Q greater than 1. And then a few steps, I don't think I brought those details. No.
Okay, but Q is related to eta 2.
So directly from Q we can construct the here is specifically the eta 2 is constructed by this output. Let's say it's the output power over the input
Okay.
So that the what we call output current and the input one, and we get this inequality directly from the Q. Actually, if Q is greater than 1, so you can see just by organizing it, because Q was a ratio of the it was a relative currents and the ratio of relative currents. So this is really just saying Q is greater than 1, and then we get the right-hand side.
Okay, I see. And you said that this was valid in the linear response regime because you used exactly the Onsager coefficient to derive it, and outside the linear response regime, this is what you said, that you only have numerical results far from equilibrium. Yes, but
yes, in that paper, indeed, I mentioned there is now on the archive study with Matthew and Naim. And it shows, but it's really moving slowly towards proving more examples where it holds far from equilibrium. So what I can mention, you can see in the illustration what we did here was to think, for example, what if I have collection of absorption refrigerator of these quantum systems that are non-interacting? So whether this bound holds for them, and we could show some, indeed, the upper bound, we could prove it, the lower bound, we could prove in some cases.
Okay.
So in this study, we could prove more for collection of non-interacting components in the work. For example, for thermoelectric junction, it will be collection of quantum dots where each of them allows the transport.
Okay. Thank you. And I have another question, if I can. So for this, sorry, now I just forgot. I passed my. I will come back if I remember. So it was about Q, but okay, no matter. I will find it again. Sorry.
Okay. Thanks. Rafael has a question.
Can you hear me?
Yes.
Okay, good. Yeah, thank you. Thank you, Dvira, for the talk. Very, very interesting. I have a question related to the last part of the reaction coordinate. If I understood, when I've heard about this subject, one of the two effects that I more or less understood is that when you do this reaction coordinate, on one hand you renormalize the position of the levels, no, and also you get some broadening of the coupling, no, so some kind of Lorentzian dependent coupling to the.
So right away, the reaction coordinate gives us, I mean, if we do the transformation, it's just a new harmonic oscillators added to the model. We don't see right away any renormalization effects. So we have the original levels, additional harmonic oscillator extracted from the cold and warm bath, and they're coupling to their own residual environments. So here
sorry. So the problem is, so basically what you do is to affect the coupling. So more the questions, my question is, how much does this affect the filtering of each bath to the different frequencies of the system? So can this make the different baths affect the different transitions? Or
okay. So great question. Indeed, I didn't talk about. Oops, I didn't talk about it. I need to show it. So that's as you can see, there are different regions here. I didn't elaborate. So there is a cooling, which is a colorful, but then there are other colors. So whatever is not colorful is not cooling, but for different reasons. For example, region R2, it's because exactly the effect you mentioned at a different bath. Now we get heat dumped from the warm bath towards a cold bath. So it's like what we call maybe leakage, internal leakage between the bath. So we do see these effects showing up. So it's not just renormalization of parameters. I shouldn't. Thanks for the question. There are other effects. So that's indeed, we can see here, and also the top gray, it's about how the levels moved so much that it's just, it doesn't resemble anymore an absorption, this original design of that we had. So there is also no cooling, but for trivial reason, because the levels are not organized in the correct form.
Okay, okay, thank you.
Just taking the advantage that we are in this figure, I noticed that maybe it's related to what Rafa was asking, that by using the strong coupling method, you see a slight difference also in the weak coupling limit. So, you know, this gray region starts right from the bottom. So should we, I mean, I would have expected that the two methods will give exactly the same results in the weak coupling limit, but it seems not so. Who should we believe?
So we did have cuts in the paper. At weak coupling, they do agree. It's just that, so they start in the same, yeah, they do agree. Lambda equals 2 related to the other parameters is already not small. But yeah, once we go to smaller lambda, they do agree. Okay. We tested the method also on the spin boson model, and again, the small coupling, they agree, and then we start to see deviations.
Okay, I see Geraldine got her question back.
Yes, indeed, thanks. When discussing this ratio Q, you said that, okay, when your quantum absorption fridge is working, Q is larger than 1, larger or equal than 1. I was wondering, do you know how Q behaves for different tasks, for instance, heat rectification, or do you think we can make also statements for different tasks?
Interesting. So if it's not an engine, just a rectifier, or
for instance, if it produces quantum correlations, well, you see there are different things, and I'm wondering if you looked at it or not.
No, we didn't look at it. Yeah, it's an interesting point. So we have the main point, yeah, as you mentioned, we have different currents in the system. They have their fluctuations, and the question is a relative ratio, the ratio of these fluctuations. Which one is more noisy?
Yes.
And we didn't look at it. Yeah.
Okay. No. Okay. I will say maybe I contact you because we have also something. So, thank you.
Thank you. Okay, thank you. I think we have gone beyond the time. Let me see. I see yes. Daniel says beautiful talk.
Thank you very much. Thanks
But
again.
No, I don't see more questions, so maybe I skip mine. And I just want to thank Dvira again for the very nice talk. And thank Takiro also in the morning. And thank you all for